And welcome back. We are continuing our unit in rotation, working with a physics or an AP Physics C mechanics class. This topic that we're going to be talking about is called the parallel axis theorem, and it coincides with topics that we have been talking about related to moment of inertia. So I've done some screencasts on moment of inertia already, and this is a skill that you're going to need to be able to use as you're solving problems in our rotation unit. It is not that tough of a skill. You have done harder things so far in this unit, and once you get used to this, you're going to see it's actually quite easy. But we need to talk about it. Let's go ahead and develop that skill. So the first thing I want to do is ask a question. If we were going to calculate the moment of inertia of an object, would it matter where we made our origin? Pause for a second and think about this. And I hope you can see that the answer is going to be yes. In other words, if we make our origin here in the center of a sphere, let's say somehow we have, I don't know, massless sticks that go through a heavy sphere, heavy solid sphere somehow, and we're able to rotate it about the center, that's going to be easier to do than if we had sticks on the outside, more or less massless sticks on the outside of a heavy sphere, and try to rotate it this way. It would be just a different rotation. It would be harder to do with the example on the right than it would be with the example on the left. What that means is they both have different moments of inertia, and the key difference between these two is where we put our origin, or you could say where we start our rotation from, because in these cases they are one and the same. So we're going to rotate from the center over here, or we're going to rotate from the edge over here, and that will change the problem and our understanding of the problem. Okay, and so one thing I need to remind you about is the idea when we're doing a compound moment of inertia calculation, meaning we have multiple simple objects that we know are moment of inertia equations for, and we're putting them all together in like a compound system. Whenever we do that, we need to measure all of the distances to the same reference point. So in this drawing right here, you would measure all of the distances from the central axis rotation point right here, let's say. If I change the problem and made this the axis of rotation and our zero, you could say, on our x and y axes, that would change the problem. And we could do that. We would just have to make sure everything that we're using, like this sphere, this horizontal bar, and this vertical rod, all three of them were in reference to this point now. So you wouldn't do some in reference to this point here and some in reference to this point here. If you did, you would get the problem wrong. So just as long as you can remember, keep all of your distance measurements to the same axis point as you do the problem, you're going to be totally fine. All right, and so what is the parallel axis theorem? Well, here it is. We're going to say the total moment of inertia for a system depends on the moment of inertia for the center of mass of an object. Like we have just a simple object over here, the sphere. So it could be a simple object that we have right here, or it could be a complex object made up of multiple simple objects that would be included in this moment of inertia value right here. In addition to that, we're going to add an offset value. This offset value is going to be mr squared. This equation right here is not on your equation sheet, but you need to know it. Please memorize it for your AP Physics C mechanics test. You will need to know this. And one way to remember this is that mr squared function is exactly the same as all of the other regular simple shapes that we've worked with so far. They're going to be all of the same structure, mr squared. They have some fraction usually out in front, but then they have mr squared. So looking at this another way, we could say our total moment of inertia from some reference point is equal to the moment of inertia for the center of mass for the simple or a compound object plus the additional moment of inertia due to the distance between what I'm labeling as your 0 point and the center of mass. So O and C, or 0 and C over here. And the parallel axis theorem does have different names. And so sometimes it's called Steiner's theorem, for instance. And so what I would like to do is actually work this out and see what it would look like for this very simple scenario that I just created. All right, so we take a look at this. Our total moment of inertia is going to be equal to the total moment of inertia for the center of mass. So for the object, either compound or simple, plus the offset value. All right, well, we know for a solid sphere, we'll assume this is a solid sphere over here, for the moment of inertia for a sphere, plus we're going to add our offset value over here. Then we can find a common denominator and simplify the problem, and we end up with a total moment of inertia for this of 7/5 mr squared. Now hold up there, don't just move on when you get an answer. This is a good example of you should think about whether or not your answer makes sense. So does this make sense? Well, if you remember some of our other equations, this is actually relatively high compared to some of the other things we've had. And does that make sense? The answer is yes. In other words, it would be a lot harder to rotate this system over here if we're rotating about this point than it would be to rotate this sphere if we were rotating about this point. The higher moment of inertia shows that it's going to take more torque to accelerate that object. Essentially, it's going to be harder to rotate that object if it has a greater moment of inertia. So our answer does make sense. Let's do one more example and we'll be good. Okay, and so I'm going to let you read this problem right here, but essentially we're saying, all right, let's take a rod right here, and we're going to start from rotating like is shown in this picture right here, and we're going to offset it. We're going to offset it by half the length of the rod, and we're going to rotate it over here. And so we'll start with this equation, and hopefully we will end up with this equation over here. So that's essentially what the problem is asking us to do. So let's get started. All right, I'm going to start by writing down this equation. I just want to reiterate that you're going to need to memorize this equation, but once you get used to this, it's really not that hard, and it will not be hard to remember this term over here. All right, and so next we go ahead and plug in what we have for this original value. So we're going to say, well, what is our moment of inertia for a rod that's rotating about its center like this? And the answer is it's going to be 1/12 ml squared. So notice we're changing the r to an L in the context of what we're working with. And we're going to add this over here. This is our offset value. Notice that we're going to have m, we still have the same mass, L over 2. Why L over 2? Because we have offset by that much. We've offset by half the length of the rod. And that is all in here. And we need to square that entire value. So we're going to square that entire value. We end up with 1/12 ml squared plus 1/4 ml squared. I'm going to label that as equation 1 and drag it to the next slide. And so we continue with the problem. If we take a look, we just continue to simplify, and the problem simplifies out to 1/3 ml squared. And that's where we were trying to get. And so we've used the parallel axis theorem to prove that you can go from one simple equation that's used for rotation to another, and you can actually prove that using the parallel axis theorem. If you've been able to follow along up until this point, that is great, because this is a skill that we're going to be using in future problems throughout this unit. It's really not that tough to be able to learn this, and you can do this. I'm going to continue with some more screencasts, so hopefully you stick around for some more. Thanks for listening.